Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel, we cover all things Gen Chem related. In this video, we're going to be starting chapter 6, which is going to be focusing on energy and thermochemistry. Let's get started. So chapter 6 is focused on understanding this big word known as thermochemistry. And so if we break that word down, it's really looking at the energy that's associated with these chemistry processes that we've been talking about up until now. What we're going to learn is as we are converting things from physical, different physical chain states like solid, liquid, or gas, or actually doing chemical reactions, there is a thermal property, this energy property that has to be transferred either into the system or out of it as we go through it. So this section is really just to help to lay the foundation for this wide range of topics known as thermochemistry. And so we talked about energy briefly in chapter 1, and we will remember that energy affects all type of matter. So when we're studying the behavior of matter, energy plays a huge role in that. So energy is defined as anything that has the capacity to do work. And if we break that word down even further, work is a force acting over a distance where energy is equal to the work, which is equal to force times distance. Now, the other way that energy can be transferred is through heat. Heat is the flow of energy caused by a difference of temperature. And remember that when you put objects in contact with one another, there's going to be an energy exchange that occurs, whether it's leaving from one object to the other or vice versa. And often this can be viewed or thought of as a form of a collision. So as we're going through this chapter, I want you to think about energy as an object or a quantity that you can possess. And so think of it kind of like money. We all try to possess money. We all exchange money daily, whether we're being paid, so money's coming into our bank account, or we're paying it out, money's leaving our bank account. There's always this exchange that's happening around us. So think of energy as a quantity of an object that you can possess. And the two main ways that we can exchange this energy is through producing some type of heat or requiring some type of heat, or doing or producing some type of work. And these are the two main ways that an object can exchange energy with other objects around it. And remember, the flow is either going to be going into an object or out of an object as we're studying this. So there are a few basic classifications or basic vocabulary that we want to ground set ourselves with. And so we can take energy and further divide that into the type of energy. And so one type of energy that we learned back in chapter 1 is kinetic energy. Remember, kinetic energy is the energy of motion, or it's energy that's being transferred from one object to another. And a good example of this in the chemistry realm is thermal energy. So thermal energy is that energy associated with temperature. And remember, thermal energy is a form of kinetic energy because it's constantly in motion, going from areas of high temperature to low temperature. And so you can see on this diagram here that the energy associated with that cue ball is being transferred in the form of work to the purple ball and putting that purple ball in motion. And so again, this is an example of kinetic energy. The other main category of energy that we talk about is potential energy. Now, potential energy is the energy that is stored in an object or an energy associated with the composition and position of the object. So it's the amount of energy that's internal, innate to that object. And we're going to learn that a lot of that has to do with the types of chemical bonds that are found within that structure. And so you can see, just like we discussed before, you can transfer from one form of energy to another, in this case, going from potential energy to kinetic energy by allowing that ball to be placed into motion. So again, if we think about the overall breakdown of energy, energy as a whole is the capacity to do work. We can subdivide that into kinetic energy or potential energy, and then further categorize those as being either thermal energy, which is the energy associated with temperature, or chemical energy, which is that associated with the positions of electrons in the nucleus. Now, there are a lot of different types or forms of energy that you're going to encounter as you embark on your chemistry journey. We'll touch on a few of these throughout the remainder of the class, but I did want to just show you them so you're familiar with them. So the first type is electrical, and that's the energy associated with the flow of electrical charges. There is heat or thermal energy, and we're going to talk a lot about that in this chapter. And that's, again, the heat associated with molecular motion. Light or radiant energy, we're going to deal with that in chapter 7. And that's the energy associated with transitions within an atom. There's nuclear energy, which is the potential energy that's stored in the nucleus of an atom. And then there's chemical energy, which is the potential energy due to the structure of the atoms, the attachment between atoms, the atoms' positions relative to each other in a molecule or the molecules, and relative positions in the structure. So much like before, energy is going to observe the law of conservation of energy, which means that energy cannot be created nor destroyed. So what happens is, rather than creating some new form of energy or destroying this energy, it's merely transferred between objects from one form to another. In this example, we're showing where this mechanical potential energy is being transferred into kinetic energy to put that ball into motion. But the total amount of energy that's present at the beginning must be equal to that that's present at the end. So something that's really important in this chapter is understanding the direction in which energy is flowing. And so we're going to be talking about things in regards to something that's called the system, or the thing that we're studying, and then everything else that's around it, or what we call the surroundings. So as you can see in the diagram, energy can be flowing one of two ways. It can be flowing from the system out to the surroundings, or from the surroundings into the system, much like your bank account. So just like your bank account, you can have money being placed into your bank account. So that's coming from the surroundings into the system. And you would expect that that value would end up being a positive value in your bank statement. Or you could have energy leaving the system out to the surroundings, like you're paying something out, and then you would see a negative value associated with your bank statement. So keep those in mind as we go throughout this chapter: system versus surroundings. The system is the thing that we are studying. The surroundings is everything else around it, and energy can either go from the system to the surroundings or from the surroundings into the system. So we have to be aware of who's the system, who's the surroundings as we go through this chapter. And we're going to be studying this exchange of energy between these two pieces. Now, a good representative of this law of conservation of energy is shown for you here. And so remember that we can always have energy that is neither created nor destroyed. We're simply either transferring it from one object to another. So what the conservation of energy means is that the amount of energy gained or lost by the system has to be equal to the amount of energy lost or gained by the surroundings. They're going to be equal but opposite. What I gained, you've lost, or what you've lost, I've gained. So it's going to go back. They're going to be similar to one another. And so if you look at these energy gauges that are shown for you here, notice on the left, we have the system energy gauge. On the right, the surroundings, and you can see where they're positioned at before the actual process occurs, right? So if you look at the gauges, now after this energy process has occurred, notice that the system has lost some energy, and that same amount of energy has been gained by the surroundings. So the system is in the negative, the surroundings are in the positive, but the two are equal but opposite. Now, for this chapter, you do want to be familiar with the units of energy. Be able to be on the lookout for what you would want to identify as an energy unit. And so the amount of kinetic energy an object has is directly proportional to its mass and its velocity. So you could calculate the kinetic energy. And when the mass is in kilograms and the velocity is in meters per second, the unit for kinetic energy is kilograms times meters squared divided by seconds squared. Well, the way we refer to energy, or what we look for in this unit, is the unit of a joule. A joule is equivalent to the amount of energy needed to move 1 kilogram mass at a speed of 1 meter per second. And so what we're really going to be looking at is the joule. Anytime you see a joule, and again, you could apply those metric system prefixes, millijoule, kilojoule, but the joule is our base unit that we're going to be referencing throughout this chapter. There are some other energy units that are out there. Likely you've heard about a calorie before. And so the calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. Now, what's interesting is, although we call them calories when we think about what we're eating, the food Food calories are actually what are considered to be kilocalories. And so it's the energy needed to raise 1,000 grams of water, 1 degree Celsius. And we can easily convert from joules to calories, or even this other unit, which is kilowatts, as needed. And so the conversion factors are shown for you here. And then just some FYI information that's found for you here when we talk about the common amount of energy that's needed or is shown here. So you can definitely peruse this at your leisure. So now we're ready to get into some of the laws associated with thermochemistry, and more specifically, the first law of thermodynamics. Well, the great thing is we've already learned it. The first law of thermodynamics is the law of conservation of energy. And that is basically saying that the amount of total energy in the universe is constant. We can never create a system that would continuously produce energy without some source of energy. I mean, just think about it. If we could, we would have cars that would not require any fuel to keep it moving. So again, the total amount of energy that's in the universe is constant. So what the system gains or loses is equal to, but opposite what the surroundings gains or loses respectively. And so again, we can see that if we go back to that gauge image that I showed you a few slides ago, where we see that the overall energy that is being maintained within this transfer is equal to one another. So there's no real difference between the amount that's present, because one has lost it, so it's in the negative, one has gained it, so it's in the positive, so they're equal but opposite. So if we were to add up the overall changes in energy, so anytime you see this symbol, this triangle, that triangle just means the change. So you're taking the final amount that you have minus the initial amount. So anytime we were to add these up, it should add up to 0, because again, the energy change in the system is equal but opposite to that of the surroundings. So the overall change is 0, constant energy in the universe. So the way that we're going to be measuring and monitoring energy in this chapter is something known as internal energy. The internal energy is the sum of the kinetic and potential energies of all the particles that compose the system. Now, the change in the internal energy of a system only depends on the amount of energy in the system at the beginning and at the end. So this is considered to be what's called a state function. So a state function is a mathematical function whose result only depends on the initial and final conditions, not necessarily how we got there. And so for our purposes, when we're referring to the energy, we're going to call it delta E, the energy of the reaction or of the surroundings. And that's going to be equivalent to the energy affiliated with the products minus the energy of the reactants. So to help you get a better idea of what state function means, you can look at this image here. And so this image is a big mountainous trail that you can go up. And you can notice there's two different paths. There's path A, which seems to be a lot longer. You're definitely taking more of the scenic route, maybe stopping for a few pictures here and there. And then there's path B, which looks a little harder. You're going straight up the hill, definitely probably more rigorous. But at the end of the day, regardless if I went path A or path B, the total elevation that I reach once I get to the top remains the same. And so the elevation in this case would be considered to be a state function, because regardless of the path that we took to get there, it remains the same. Okay, so that's the mentality we want to have when we're thinking about these topics. So the distance in this case from the base of the peak of the mountain is a state function. It depends only on the difference in elevation between the base and the peak, not how you arrived there. So again, that's the definition of a state function. Throughout this course, we're going to want to develop what are called energy diagrams. So energy diagrams are those things it's a graphical way of showing the direction of the energy flow. Is my energy leaving my system, or is it coming into the system? And the way that we draw them is indicative of such. So if we have this situation here, like you see on the right, where we say that the initial amount of energy is here and the final amount of energy is there, well, if we were to take the final minus the initial in this case, we would end up with a positive change in that energy value. So we would say that some energy has come into the system that I'm studying for it to go up. So the energy would be positive. But now if we had a situation where we had our initial at a higher level than our final, well, now if we take our final minus the initial, that change symbol, we would end up with a negative value, which means I've now let go of some energy out to the surrounding areas. And so our change in energy would end up being a negative value, okay? And so you have to think about, what am I starting with? Where am I going? And then compare the two. Okay, now let's put all that together and think about the direction of the energy flow in regards to the system to the surroundings. So remember, energy is flowing, when energy is flowing out of the system, it has to go into the surroundings. Just like when you pay a bill, it's going out to somewhere or outside of you. So you, as you're paying it, you, the system, as you're paying it, you're in the negative. And the surroundings, the person that you've paid, is now in the positive. And so again, this change is equal but opposite to one another. So the energy for the surroundings is positive, the energy in the system would be negative. But again, these would be equal but opposite processes. Now we could also have energy flowing the other way, where energy is flowing into the system from the surroundings. So let's say someone cash apps you, sends you some money. Well, now your bank account, your system is in the positive. Theirs is in the negative because they've now gotten rid of some of that energy, some of that money. And so again, you have these equal but opposite processes, positive for the system, negative for the surroundings, but the overall change is equivalent to one another. Equal but opposite. Okay. And then last but not least, we want to put this in terms of how we would apply an energy flow diagram to a chemical reaction. And so if we had this chemical reaction here where we were allowing carbon dioxide to decompose into carbon and oxygen, or the reverse of that, where you have the carbon and oxygen coming together to create carbon dioxide, we can think about what kind of energy change is associated with either of those processes. So the total amount of energy in 1 mole of carbon and 1 mole of oxygen is greater than the internal energy in 1 mole of carbon dioxide at the same pressure. And so in a reaction where we had our reactants as our carbon and oxygen and the product as carbon dioxide, there will be a net release of energy. So let's look how we break this down. In this example, carbon and oxygen, those represent our initial states. And then CO2, that represents our product. That's the final. And so now if we were to do a look at the change in energy that occurred here, well, our final is now less than the initial. So we would say that in this case, if we took final minus the initial, that we would end up having a negative value here, which means there's a release of energy into the surroundings. But if we were to reverse that situation, where we then now made, instead of that being our final, we now made this be our initial, we're starting it as a reactant, and these two become the products, this decomposition reaction. Well, now if I took my final minus the initial in this case, we would end up with a positive value. So that means the energy is coming into the system. Okay, and so we can use this to predict which direction is the energy flowing. In the case where you're having a positive value coming into the system, that means the surrounding area is getting cooler, there's less energy there, the reaction itself is going to get warmer, and vice versa. If you're letting go of energy, the surrounding area get warmer, and then the reaction itself would get cooler. And so we can see that shown here for us, where in the first scenario, we had energy being released. And in the second scenario, we had energy being absorbed. I hope this information helped you ground set and understand about energy and the basics of thermodynamics. Make sure you guys comment, like, and subscribe, and let me know what other content you want to see. Be sure to check back in on some later videos. We're going to be delving into more energy topics soon. See you guys later. Have a great day. Bye-bye.